Hello, everybody. We are testing non-conventional airfoil geometries. My name is Cameron Chenard, and in my group we have Nathan McCulley, Taylor Murch, Aaron O'Connor, and Nick O'Brien. Before we begin, we'd like to give a big thank you to Professor Huber, Hubert Balan, and the Makerspace staff for all the help they gave us along the way.
Our objective is to test non-conventional airfoil geometries to see their effect on stall angle. The airfoils tested, starting from the left here, are a NECA 2412 airfoil, trailing edge sawtooth seen here, leading edge wing fence, and finally leading edge tubercle.
The test was set up by mounting the airfoil on the airfoil bracket inside the wind tunnel. After the force balance had been calibrated, the wind tunnel was then turned on and lift coefficient was measured at different angles of attack until stall was achieved for each airfoil tested. Several difficulties our group faced throughout the semester included print times, print quality, and wind tunnel availability. All these roadblocks were overcome. Shown in the image, the leading edge wing fence airfoil, which had the worst quality printing.
The coefficient of lift versus alpha curves were plotted and shown here. The leading edge tubercle showed the highest stall angle at about 17 degrees. At this point, it had the highest coefficient of lift of any of the airfoils. The next best performing airfoil was actually the Control NACA 2412 airfoil. It showed consistently higher coefficient of lifts than the sawtooth and the wing fence. The sawtooth was the next best performer. It was slightly below the NACA 2412, but it showed a much higher drop off once it actually realized stall. And the worst performing was the wing fence. It realized stall at the same angle of attack. However, it was performing much worse in terms of the absolute value of the coefficient of lift. However, the stall that it did realize was much less drastic than the other.
To examine the error in the team's experiment, a test using a profilometer was used to analyze the airfoil's print surface roughness. Shown in the figure is a graph displaying millimeters versus micrometers of the airfoils. The amplitudes show how rough the surface of the airfoil is. The wing fence had the highest frequency, which led to the largest error. To conclude the team's experiment, the leading edge tubercle airfoil showed to have the greatest stall angle and therefore had the highest coefficient of lift. Overall, the experiment ran smoothly and the team was able to gather effective results.